Sophia. Oops. Yeah, so hi everyone. My name is Matt. Let's make sure this works. So we're talking about Anaconda, GPUs, and ecosystem. And yeah, disclaimer, I don't know very much about GPUs. The last CUDA code I wrote was around 10 years ago. I think that things have changed since then. I recently moved to NVIDIA from Anaconda. My new colleagues are far more qualified to give this talk than I am. So any tough questions, please go see them. So yeah, I'm also going to probably say some wrong things. I'm not an expert in this field. Don't trust what I'm going to say. I work a lot in Python, and I work in the sort of general PyData stack. These are some slides taken from Jake Vanderplas's keynote in PyCon 2017, where he talks about the sort of multi-layered stack, where you have Python at the core, you have some sort of core numerical libraries just beneath, just above that. You have a variety of other libraries for different sorts of algorithms on top of that, and then a variety of other more algorithmic or domain-specific systems. This is what people often call the ecosystem. There's hundreds or thousands of packages designed for a variety of different kinds of problems to solve. No matter what kind of scientist or analyst you are, there's probably some package that was designed for you with great care. My goal previously, and continuously, was to parallelize these with a library called Dask. I've worked on that, sort of refactoring the ecosystem a little bit to parallelize it for a while. So generally speaking, PyData has a lot of strength. It has a lot of diverse packages that are all based on a common core of libraries like Numpy, Pandas, and scikit-learn. So if we throw in GPUs, we would want to do that because they are very fast. There are things that they can do that are significantly faster than what are hard to do with other hardware. As a couple of examples, we can look at NumPy and CuPy. CuPy is a NumPy-like library that runs on the GPU. It comes out of the Chainer deep learning framework. That happens to fit the NumPy API pretty well. So here we're doing a matrix multiply and summing up some numbers. And on the NumPy side, it's around 50 milliseconds. And on the CuPy side on the GPU, it's around 6 milliseconds. So just to highlight those a little bit. So you get about an order of magnitude increase by changing an import and giving NVIDIA some money. When I first thought about GPUs, I always thought of them as being very good for dense matrix multiplies, things that are very compute intensive, very regular, very strided, the kinds of things we see in deep learning, but not other problems. I was very surprised when I saw Rapids, libraries like cuDF, which implements a subset of the Pandas interface, running on GPU. They're able to get the same order of magnitude speed increases, but on problems that were very, very different from matrix multiplies. Things like CSV parsing, which is sort of as far as you could get away from dense matrix multiplies. So there's some power here to using GPUs, but there's also a lot of challenges. Right? We have this ecosystem, and if we take out things like NumPy and Pandas, a lot of the ecosystem goes away, because it depends on libraries like NumPy and Pandas. We're left with some things that are still very good, things like Jupyter for user interaction, plotting libraries, those are still around. There's some parts of libraries like scikit-learn or Dask are still useful, or Numba or Cython, because they can be used with lots of things. Maybe Dask array or Dask data frame don't work, but the Dask late or Dask futures do work. In scikit-learn, you can't use random forests, but you could use hyperparameter optimization. That doesn't require hardcore computation connection. So this is the challenge, right? If we add GPUs, suddenly we lose the compute parts of our stack. We have to rebuild all of them, and that seems sort of untenable. We do, however, have lots of GPU functionality. The rise in deep learning has given us lots of large tech companies who build very intense frameworks that have very optimized CUDA code inside of them. Unfortunately, these frameworks aren't really designed to work well together. They're very much designed to do one thing on their own. It's actually hard to just install them together in the same place. So we have this, on one hand, we have this sort of ecosystem of projects that are really well connected. It gives us a lot of ability to mix and match. We have this GPU power. We have all of these libraries written, all this code written, but it's very hard to integrate them together. And that's sort of, I think, the tension that we face today as a community around integrating GPUs. Lots of functionality, lots of promise, not really any effort to integrate things. So I've been doing that a little bit, along with my colleagues at NVIDIA and the Rapids team. And this is just sort of mostly a talk about the kinds of things that we've run into, mostly me complaining about things I think are broken from a Python user perspective, and a couple of things that we're trying to do to fix things. Stack doesn't support GPUs. But if we add in a couple pieces, maybe swapping out NumPy for some GPU array library and swapping out pandas for something like cuDF, maybe if we're do a lot of work around protocols and conventions, we can heal out the rest of the ecosystem and get some of these things back. And that's the goal, right? Take some of these core libraries and do some magic to get the rest of it working again. So, not possible today. Definitely don't believe the last slide. Definitely not true. If you took pictures of it, please delete those pictures. Don't tweet them out. That's a fake promise. But we're going to talk about why. So what we would like to do something like conda install a bunch of GPU libraries and a bunch of existing libraries we care about. Then we might, read in some images from a library like PyTorch. Maybe PyTorch has a GPU image reader, for example. Right? We then want to call, maybe TensorFlow has a better FFT. We'd like to combine those two frameworks. Then we might want to combine them with some scikit-learn model. How can we integrate those things together? So we want to install libraries consistently. We want to pick out just functions out of frameworks, not like the entire thing. I don't want to have to create a TensorFlow pipeline or to create just to use a small bit of functionality. I want to interleave those frameworks together. I'd like to integrate with existing libraries. So some challenges we'll go through. There's divergent APIs. We actually saw this a little bit in the keynote this morning with Francois's talk. Installation, there's a lot of installation packaging woes I'll mention briefly, although you should talk to more experienced people than me. Talking about mixing functionality between frameworks and how we can sort of get that going. And managing memory between frameworks. That ends up being a real pain point today. Okay. So diverging APIs. So here's NumPy and here's Torch. I'm doing more or less the same thing. The APIs are very slightly different here. They don't need to be. Like it's a little sad that this is the case. If we're writing code that wants to be sort of agnostic to both systems, it'd be very nice if they added the S onto the end of keep dims, or kept dim as axis. Some degree of uniformity is useful when swapping things out. And there's been some sort of attempt to be NumPy-like, but those small bits that stop us from having full uniformity actually become very challenging when we're writing software on top of these frameworks. So using just PyTorch, you're fine. If you want to use something and build on top of PyTorch and possibly on top of TensorFlow and on top of NumPy, then those lack of uniformities become very, very painful. And it results in code that looks like this, right? If my object is a NumPy array, do this thing. If my object is a Torch array, do this other thing. If my object is a TensorFlow tensor, do this other thing, and so on. And it makes it difficult also if some other person comes by, maybe Google comes in with a TPU NumPy library like JAX. Now all the code has to be modified to also support JAX. Or if someone comes in with some quantum NumPy in the future, we're going to need to modify all of our code to do that. So it's very nice if people remain uniform to APIs, or at least agree on some sort of protocol, so we can extend the ecosystem in the future. Installation inconsistencies. If you run the 2 lines of code, you'll get some fun results. So I installed PyTorch from the Nightly channel. I then installed TensorFlow, which uninstalled PyTorch. This actually isn't TensorFlow's problem. This is my problem with Conda. But we downgraded Python. We removed PyTorch. It was actually, we couldn't install these 2 together in the same environment. And again, this is not anyone's fault. It's just that this hasn't been tried often enough that we haven't identified and resolved this problem. Additionally, in building, so this is some excerpts from an Arrow developer mailing list issue that went on for a while. If you're familiar with this issue, you are groaning internally right now. There's a standard with pip packages and wheels on how to package up binary libraries. There's a many Linux standard, which neither TensorFlow nor PyTorch support. It makes it hard if you want to install multiple libraries together. If you want to pip install Arrow and pip install TensorFlow, things break in very uncomfortable ways. And so there are some standards, and we're not doing a good job of adhering to those standards, and that causes a lot of pain. So sharing data between libraries. So this is some code that we would often write. We'll create a pandas series. We'll then call the NumPy function, maybe NumPy exp on that series, and that works. Like, this code is not surprising to people in this room. But let's recognize that we're calling a library function from one library on an object that was defined in another library. And somehow that manages to work. we've all sort of assumed that works. We can call static image functions on pandas series. We can call all of our different libraries can work on all of our different objects. If we do the same thing with, say, two deep learning frameworks like CuPy and Torch, or TensorFlow and Torch, or whatever you like, we'll get a type error. CuPy does not understand what a Torch tensor object is. So if we switch them, so now we're creating a CuPy array and calling a Torch function, Torch also doesn't understand what a CuPy ND array is. So this inability to mix and match stops us from being able to sort of pick and choose our functionality and mix. We have to stay either in Torch land or in TensorFlow land or in CuPy land, and we're forced to build on one of those stacks. But we would like to, with Rapids, we would like to read in some CSV data maybe, then call an FFT on that data. We would like to be able to use some other library's FFT function. We don't want to make our own. Right? So we need this ability to start mixing and matching, especially if we start having full pipeline GPU computations. Problem n+1. So even if we were able to move data back and forth, each of these libraries has their own memory manager. So CUDA malloc is slow, so everyone else built their own memory pool. So if you ask for data, they ask for more data, and they hold on to that. So if TensorFlow starts working, it will eventually hold all of the memory of your GPU. If you then import something else, like Rapids, for example, or Torch, or some other framework, TensorFlow is still holding on to all the memory. TensorFlow expects it is the only framework running on your GPU. And PyTorch and Rapids and lots of other libraries do the same thing. Whoever's there first gets the data, which is awkward if you have an array in one framework and you want to send it over to the other. So what would be much nicer is if we had a shared memory pool where we could allocate data generally in a shared space. And that might be allocated by Rapids. Maybe we load from a CSV file. Then we pass that array over to something like TensorFlow or PyTorch or Chainer in order to do some deep learning. That's like a reasonable thing you'd want to do. We do this all the time in Pandas and Numpy. We would read a CSV file and then hand it over to Numpy to do some work. But this is not the case today when we're trying to mix and match frameworks. So this isn't new. This is, again, how we're used to thinking. On the CPU and normal memory, we all sort of just use malloc and free, the same memory management, and everything works fine. But it's somewhat hard to motivate. It's actually hard to motivate TensorFlow or PyTorch to use some centralized memory manager, because that's going to make it more awkward for them in their main function, which is deep learning pipelines. So we're trying to sort of force these frameworks, these deep learning frameworks, to go sort of slightly against what they were intended to do optimally, make some sacrifices so that they can all share. So some social challenges to mix up there. Okay. The challenges aren't always with the GPU code. Sometimes it's with the existing ecosystem code. So for example, QML is a Rapids library that does scikit-learn-like machine learning, more traditional machine learning, not deep learning. And they have things like logistic regression, UMAP, lots of fun algorithms. And you might want to use something like scikit-learn's grid search. Right? There's no reason for us to rewrite grid search. That's not like a CUDA-able algorithm. It's very reasonable just to do it with the existing API. And so Rapids adheres to the standard scikit-learn API so we can make use of these existing functionality. But unfortunately, that functionality assumes that it is using NumPy arrays. So our ecosystem was designed around NumPy, and now we need to sort of undo that assumption. Right? So even if we have a very fast, maybe even faster than NumPy implementation we're throwing around, scikit-learn will always coerce to a NumPy array. We actually ran into this also with Dask. Dask also has a NumPy-like array, this sort of distributed array. And it's sort of awkward. We want to use some of these functionality, but we can't because scikit-learn makes some assumptions. And the scikit-learn team has been awesome, actually, about undoing these assumptions. They're very willing to edit things and to modify things and to make things more generic. But that is a process, and we're finding out a lot of things like that. So these barriers, was mostly done complaining, then I'll switch off to fun things. These barriers fracture the ecosystem a little bit. If you're writing new code, if you're writing a new library that uses one of these libraries, you have to choose today. Do I build on TensorFlow? Do I build on PyTorch? Do I build on CuPy? And people are making those choices. Two examples, PyMC3, a library for Monte Carlo simulations, used to be based on Theano, an old deep learning framework. Theano is now retired. So they had to choose. They had to choose a new one. And they were deciding to choose and build off of TensorFlow, which makes sense. TensorFlow has some awesome functionality that they really need. But future PyMC4 users will be in TensorFlow land. At the same time, systems like FastAI are focused much more on PyTorch. They're in PyTorch land. If you wanted to use FastAI and PyMC4 together, you would be in an awkward situation today. We're now building two different ecosystems, and that's tricky, right? If we want to sort of have the same mix and matchability we've always had of, you just want to import scikit-image and import h5py and import matplotlib and sort of throw those together, we can't do that anymore. We need to choose what it is which land we live in. So these are the challenges we're trying to sort of address, and we'll talk now about some solutions. Thank you all for listening to me complain for a while, and hopefully I didn't say anything too egregiously wrong. So some awesome things. API compatibility. So here's some code that people in this room I suspect understand. Here's some pandas, NumPy, and UMap code. UMap is an awesome scikit-learn-like algorithm. And you can, with an import change, run those on a GPU using libraries like cuDF, CuPy, and QML. Oops. Right, the change here is small. If you have a GPU and you understand the current stack, in some cases you can just switch and you'll be fine. Right, and that's powerful. That means we don't need to retrain people. We don't need to learn how to write CUDA. I don't need to learn how to write CUDA, which is even better. So we can maybe start applying these sorts of technologies to new problems that we have. And this is due in large part due to some care in some of the design of those libraries, and in some of the older libraries like NumPy becoming more generic. So as of NumPy, the last release, you can now add a flag so that any NumPy function, like NumPy here, can be used with any NumPy-like library. So here we're using it with CuPy. There's also a sparse library, just sparse n-dimensional arrays. There's Dask array. You can make some future library. And in all cases, this NumPy exp function just works, right? And this works for now any NumPy function. So what this means is that a lot of code that was written around NumPy can now sometimes start to seamlessly work around other libraries, like Dask arrays or CuPy arrays or PyTorch arrays. I'm going to show a quick example of that. So here I'm sitting on a DGX, which is a machine with a 40-core CPU and 8 GPUs. I'm going to create a Dask array. So this is a bunch of NumPy arrays spread across memory of that machine. And I'm going to do an SVD. So Dask array has a fairly sophisticated SVD algorithm in it. I'm showing the graph here. Let me expand that out a little bit. This is probably not super visible, but every little point in that graph is some linear algebra function running on some NumPy array. And if you do all of those functions and you transfer data as the lines suggest, you will eventually get out an SVD algorithm. No idea how it works. Someone smarter than I wrote it. But Dask has these sorts of algorithms in it. It has very complex code to do a large SVD out of many small QR decompositions and other things. Let's run that. This is running on a 40-core CPU. Let's also open up the task graph. So we're going to wait here a little bit as this runs. It's going to be a little bit awkward. We're just going to sort of feel that. So we're doing a bunch of QR decompositions. They're taking 2 or 3 seconds each. Then we're going to do sort of a smaller SVD computation in the middle. That'll take a few more seconds. Then we'll do a bunch of other things. There we go. It's almost done. Hooray! We've just done a big SVD using a multi-core CPU. This could have been on a cluster. It would have been fun. Or we can do this. So CuPy, again, is a GPU NumPy implementation. And we can switch out. So instead of making a bunch of NumPy random arrays, we'll make a bunch of CuPy random arrays. And we'll run that. So we're making our data. And we're going to compute that. So recall that when we did this on the CPU, those like QR decompositions took a few seconds each. And now if we zoom in here, we'll find that they're taking a few hundred milliseconds. So we're getting much more speed up out of this algorithm with our GPU. It then actually slows down. The latter part of this computation is much, much slower because our communication is much worse on the GPUs currently. This is actually more Dask's fault than it is the GPU's fault. We're working to correct this. But what was neat is that in both cases, we got to experiment with a CPU and a GPU and figure out which one we wanted to do without doing much work. Additionally, even more importantly, this really, really complicated algorithm, we didn't have to write over again, right? We got to reuse that same code. Dask array was not written for GPUs. It was written for Numpy. And yet, we've gotten CuPy to look enough like Numpy that we can trick Dask. We can trick a fairly complex library into thinking that the thing it's running on is a Numpy array and have everything just work. Right? So this is sort of what we get by sort of this ecosystem growth. These protocols and conventions, code we wrote before for the normal PyData ecosystem on CPUs, we can now start to reuse. And that's because we've done a lot of work with Numpy, and there's protocols that everyone's implementing and everyone's happy. So this is the hurrah moment of the talk, by the way. It's all downhill from here. There's another example I could show you, which is the same thing with pandas data frames. I'm not going to show that to you. Some other work that's happening. So sharing data between libraries. We saw this example before, where we can call a NumPy function on a pandas series. That's because the pandas series implements the _ array protocol. This is implemented a long time ago, and lots of pandas-like objects, NumPy-like objects implement it in Python today. That's why things just work. So this sort of _ something is a protocol or convention, and many Python objects implement them to do different things. We're now implementing more of those things throughout the ecosystem, and that's how this magic connection works. For example, there's the CUDA array interface protocol, which objects that hold on to an array allocated in device memory can tell you where that memory is. So libraries like CuPy use this. Also libraries like Torch implement this. These I think were both written by the Numpy developers who organized this protocol. They've been actually really awesome at doing a lot of this integration. They're sort of the first Python GPU compatibility community. And what that means, is you can do things like, so Numpy understands this protocol. So you can give Numpy any object that implements this protocol, and it can run GPU code on it. So I can create a function with Numpy. I can apply the function onto a PyTorch or a CuPy array, and everything just works. And that's cool. They didn't have to understand each other. Numpy doesn't have any if-is-instance torch tensor or if-is-instance CuPy ND array code in it. It just uses a protocol. Okay. There's been a lot of conversation around conda installing packages. So it's if you do not know much about CUDA and you conda install GPU libraries, it is very unlikely that you will get it right the first time. There's lots of challenges and lots of sort of speed bumps you're going to run into. Partly is because so you have a CUDA driver on your system, which is of a certain version, and you need to match the package that you are downloading with your CUDA driver. And every framework has a different way of specifying this. Some use little package names, some have used labels. It was sort of a mess. No one had communicated about how to standardize across this. So it turns out if you just raise an issue and CC all of the right people on GitHub, Stan will come by, Stan, one of the Numpy developers, and propose a very long but very sane solution that everyone will agree with. This happened over the course of a few weeks. Let's see. Looks like it was from February up to December. And more or less everyone's fine now. So things are better now. In the next releases of these libraries, I think PyTorch has already done this. This will now be standard. So just some communication that we're not doing, we haven't done previously. But if you just raise issues in an informative way, and again, CC all the right people, it works out pretty well. Additionally, Stan is also adding a virtual CUDA package. On your CUDA environment, you'll have a CUDA package that isn't a real package, it just sort of looks at your driver version. So conda solvers will look at it properly. Okay, so generally, by establishing conventions, we enable flexibility. People can mix and match, people can choose, new people can show up. I work for NVIDIA, but Intel could show up and write a faster pandas, and maybe that would also start to work, right? We're opening the playing field a little bit, both for users to try out new architecture and for architecture developers to have more access to users. If someone wanted to make an OpenCL Numpy implementation, for example, that would also probably just work. So there's still many, many problems. Memory management still doesn't have a clean solution. There's still some fragmentation in development. The TensorFlow and PyTorch APIs are pretty good, and it's very attractive to develop just for them. And if I were to make an application, I might select that. But that, again, has this sort of long-term bifurcating process. Some other issues. So number 4, a culture mismatch. A lot of CUDA code was not developed with data scientists in mind. Sometimes they just have error numbers rather than informative error messages, for example. Sometimes they segfault in ways that don't make us happy. So there's just some sort of cultural alignment that has to happen. Also, additionally, what I've found is working on Dask and GPUs together is that as my computation accelerates by a factor of 10, suddenly all of my overhead becomes way bigger relatively. So there's a lot of other bottlenecks that are showing up, things like communication, Python overhead, many other things. If you ask any Rapids developer what our #1 issue is right now, Keith, what's our #1 issue? Communication? Yeah, it's communication. It's network communication. We have a bunch of GPU people thinking about network communication because that's what's stopping us right now. Previously it was the CPU. Now computation is not a bottleneck. Now it's communication. After that, it's going to be scheduling overhead or something else. So a lot of other things are now becoming more apparently awkward. But fortunately, a lot of very smart and very engaged people working on them. In particular, the Anaconda Numpy developers have been amazing at this. They've been at this for years. They're a huge resource of intellect and experience. The NVIDIA Rapids team has been spinning up on this really, really actively, which is fun, and bringing sort of all of NVIDIA along with them for the ride. And the framework developer communities. They've actually been pretty comfortable and pretty happy about adopting some of these conventions we asked them to. So again, by establishing conventions, we enable architecture flexibility. And that means that we can start making some new things. And this may be the parting comment I want to leave you with. We have a ton of functionality that's really fast that we can use to solve problems. Problems outside of deep learning. Maybe curing cancer requires not a deep learning model, but just deconvolution or fast wavelet transforms. So as we start to sort of explode that functionality out into smaller pieces that we can consume and mix and match and play with a bit more, what are some good applications for that playing? Where else can we use this functionality? So that's it. Thank you all for your time.